Hello, students. Today in this class, we'll be learning a very important topic, which is drawing the Lewis dot structure or electron dot structure of covalent compounds. Okay, so whether you are an IBDP student or an AS level student, this particular topic is common in both of those um, boards, and generally, like all 2 mark question or 3 mark question always comes, and that question is basically linked to some other questions such as deciding the shape, deciding the geometry, hybridization, polarity of the molecule, right? So all those topics are interlinked, and all of those topics can only be solved if we know how to basically draw the correct structure, right? So we'll talk about that, and we'll talk about the best method that we can use to draw a particular dot and cross structure directly for covalent compounds, right? So let's start. So we are learning the dot and cross structures, and specifically for the covalent compounds. Okay, so that is what they keep asking, and that is what is having a high weightage when you talk about solving past papers. You'll find a lot of questions related to that. How do we do that? Okay, so we'll take an example of, let's say, carbon dioxide, an easy molecule to start with. And what I say is the first step is going to be find the value of Q. Now, what is this Q? Q is equal to the number of valence electrons minus the charge. Okay, so this is the formula for Q. And this Q is basically the number of electrons that we will be using to draw the structure. Okay, so number of electrons that we'll be using to draw the structure. Let's calculate it quickly. So in this case, Q would be carbon, which has 4 valence electrons, right? Carbon is 2, 4, and oxygen is 2, 6, right? So it would be 4 for carbon. There are 2 oxygens, so it would be 2 times 6. And then there is no charge on carbon dioxide, which will give us the number of electrons as Q. So Q means 16. We can use 16 electrons to complete the shell, or you can say complete the shells of all the atoms involved in the structure of CO, right? So let's see how we are going to do it. So the next step is going to be draw a rough structure. Now, rough structure is going to be your gut feel, like how your structure should look like. Doesn't need to be correct and will not be correct, but this is how the structure should look like. And if you have to draw how the structure should look like, obviously there needs to be a carbon in there in the center. There has to be an oxygen, and there has to be an oxygen on the left hand side, right? So anyone who would know a bit of chemistry knows there is going to be a carbon in the center, and there will be 2 oxygens connected to it, right? Now, after we have drawn the rough structure, we have to decide, number 3, calculate the remaining electrons which will be used to complete the shells of all atoms. Okay, so we have to calculate the remaining electron. What are these remaining electrons? So we had these 16 electrons that you are allowed to use, and we have already used up 4. How have we used up 4? Have a look. One covalent bond means 2 electrons are being shared. So 2 here and 2 here. So out of the 16, we have used up 4 electrons, right? So the remaining electrons would be 16 minus 4, which is 12. Now we have only got 12 electrons to use. And those 12 electrons we have to use to do what? We have to use them to complete the shell of all the atoms. Now let's do that. Look at the structure here. Look at this structure. The oxygen on the left-hand side just had 2 electrons right now. It just has 2 electrons, needs 6 more. Every atom needs to have 8 in the valence shell to get the stability, right? So it needs 6, we are going to give it 6. So 1, 2, 3, 4, 5, and 6. This completes the oxygen. Oxygen is happy. It is stable. The shell is complete. So out of 12, we used up 6 here. 6 are remaining. And let's just give the other 6 electrons to this oxygen. This oxygen is also done. Both of these oxygens are having a complete shell now. But the carbon in the middle is not really complete. It only has 4, right? It only has 4 electrons. How can we make it 8? We can make it 8 by converting these lone pairs to double bonds on each sides. Okay, that is what you have to do. So if the central atom doesn't have the shell complete, we convert the lone pairs into a double bond to complete their shell. And now how would it look like? It would look like this: carbon, double bond O, and then two lone pairs and two lone pairs. That is the structure of carbon dioxide. Okay. If you have to convert it into a complete dot and cross, obviously it would be like this. Two electrons from carbon being shared with electrons of oxygen on both the sides. So we are just converting this double bond into the electrons, right? So 8 electrons with oxygen like this, 8 like this for this oxygen, and also 8 with carbon. Carbon dioxide is done. And that is how we do such questions. Okay. So this was CO2, and now let's move on to slightly difficult things, or you can say slightly difficult structures. Okay, let's go. So next one that we are going to do is going to be carbonate ion, CO3, or let's do carbonate ion first. CO3 2 minus is the next structure that we are about to do. Now carbonate ion, let's calculate Q quickly. I will not be writing steps now. Let's see. So carbon is 4, 3 times 6 for oxygen minus 2. We have to subtract the charge, right? Number of valence electrons minus the charge. So that would give us what? 18, 24, 24 electrons, right? Next step is drawing the rough structure. We have to draw the rough structure. It should look like this: carbon, oxygen, oxygen, and oxygen. That's like pretty common sense. Carbon has to be in the center, and there have to be 3 oxygens connected to carbon. Remaining electrons. So remaining electrons would be 24 minus 2, 4, and 6. 3 bonds, 6 electrons being used. 2 times 3, right? So that would be 18. We are left with 18 electrons. Now let's use those 18 electrons. So 1, 2, 3, 4, 5, 6, and 8. Done. 1, 2, 3, 4, 5, 6, and 8 with the 2 bonds electrons. And then the same here: 1, 2, 3, 4, 5, 6, 7, 8. All the oxygens are done, and we have used up all the 18 electrons. This carbon is still not completed. And what we are going to do, this carbon has 6 electrons right now, needs 2 more to get the shell completed. We can convert one of those electrons into a double bond. So now it is going to look like this: C double bond O, and then O, O, and then this is going to be the same. And this is the dot and cross structure of carbonate ion. Now, the 2 negative charge that is there. So either you can do like this, you can make a box and write 2 minus here, or we can calculate the formal charge, like specific charges on each of those atoms. Those are called formal charges. Okay. So formal charges are the specific charges on each of those atoms. The formula is number of valence electrons minus number of non-bonding electrons minus number of bonding electrons divided by 2. Okay. So I'm going to mark one of the oxygens. I'm going to mark this oxygen here. This one I'm calculating it for. I'm calling it O, like first oxygen. Okay. Let's do it. Number of valence electrons in oxygen is 6, right? I'm doing it for first oxygen, O1 here. This is O1, this is second oxygen, and this is the third oxygen. Number of valence electrons is going to be 6. 6 valence electrons, right? And then minus non-bonding electrons, which are the lone pair electrons. 1, 2, 3, 4, 5, 6. 6 minus 6, right? And then bonding electron, just one bond. So two bonding electrons, 2 over 2, that will give you minus 1. So this oxygen on the left hand side, the oxygen which we have numbered as 1 is going to have a 1 negative charge. Okay. Similarly, O2, like the second oxygen, not really the oxygen molecule, the second oxygen is again going to be 6 minus 2 over 2 because it is the same setup. 6 is the number of valence electrons of oxygen. 6 is the non-bonding electron in the structure, and the bonding electrons are 2. The third oxygen, the third one, is going to be 6 in the valence electrons, and then 4 non-bonding. The third one, 4 non-bonding, 4 bonding as well. So that will give you 0. And that is how we can calculate those charges. Okay. We can do the same for carbon. 4 valence electrons, 0 non-bonding electrons, 8 bonding electrons. 1, 2, 3, 4, 5, 6, 7, 8. 4 bonds, 8 electrons upon 2, 0. So finally, we get the proper structure of carbonate ion as O minus, O minus, double bond O. And obviously the lone pairs are always there, like this, and like this. That's the structure of carbonate ion. That is how we do those structures. Okay. I hope you're able to understand uh, the sort of the process. This process looks lengthy, but it's not really lengthy. It is a very smooth process that will give you the correct structure all the time, as we have seen in CO2 and carbonate ion, right? Carbon dioxide and carbonate ion. We'll do one more quickly. That is going to be ozone. Okay. We'll do ozone, O3 molecule. How can we draw it? Let's have a look. So Q is going to be 3 times 6, which is 18. So Q is going to be 3 times 6, which is 18. So we have to use 18 electrons, not more than that, not less than that. Oxygen, single bond, single bond. That's your rough structure. Rough structure means just connect the atoms as you expect them to be connected in your actual molecule, right? So we have done that. Remaining electrons would be 14 now. 18 minus 4, right? 4 we have used. Now we have to use those 40 electrons. Have a look. So this left oxygen already has 2 electrons because of the bond. 1, 2, 3, 4, 5, 6. 8 done. 1, 2, 3, 4, 5, 6. 8 electrons done. Right? Still left with 2 electrons because 6 and 6 are used up. There were 12 remaining. So 2 are more remaining. We'll give it to the central atom. Still the central atom is not complete. It only has 6. 2 plus 2 plus 2, 6 electrons. So what do we do? How do we complete the shell of the central atom? Convert one of the lone pairs into a double bond, right? So it would be 1, 2, 3, 4, 5, 6. O, double bond O, 1, 2, 3, 4. That's your ozone. Very easy, very simple method. Formal charges we can calculate. Let's talk about the formal charge of this. I'm calling it atom A, atom B, and atom C. For atom A, it would be 6 minus 6 minus 2 over 2. 6 minus 6 minus 2 over 2. That's going to be minus 1. Valence electrons minus non-bonding electrons minus bonding electrons over 2, right? For B, it would be, there's a lone pair here. For B would be 6 minus 2 minus 2 are the non-bonding electrons, right? And then the bonding electrons are 6 over 2. So that would give you plus 1. Central oxygen will have a charge of plus 1. And then side oxygen will be 6 minus 4 over 2, which is 0, right? So the correct structure, the proper structure of ozone would be O, double bond O, O plus and minus. That's your structure. Super easy, right? I hope this is clear. Now, these kind of structures we can draw, but there's one more rule which is applicable for some atom. That is your rule number 4. When you write the rule number 4 on the next slide, that there are some atoms or elements, we can say, which can expand their octet. Okay? They can expand their octet. They show variable valency. They're able to show variable valency, variable oxidation numbers. What is the reason? Due to presence of vacant d orbitals. Okay, they show variable valency due to the presence of vacant d orbitals. Fine. So, what are those atoms? So let's talk about them. We have phosphorus, which can make 5 bonds, means it can have 10 electrons. Fascinating, right? Sulfur can have 6 bonds. Chlorine, bromine, iodine can make 7 bonds. Okay. Nitrogen can also make 4 bonds. So if possible, we will try to maximize the number of bonds made by these atoms. Okay. So if it is possible, we'll try to maximize the number of bonds made by each of these atoms. Okay. So this is very important concept which students find tricky. But if you understand this, you're getting all the structures right. Have a look. We'll draw sulfate ion. Okay. SO4 2 minus. Q is going to be 6 plus 4 times 6 plus 2, which is 32. Okay. Q is going to be 32. Okay. Then we're going to draw the rough structure. So sulfur, oxygen, 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 like that, right? Rough structure is the most expected structure that you like feel is going to be looking like, and that is what we draw here, right? After that, remaining electrons would be 32 minus 8, which is 24. Now we'll be using these 24 electrons to complete the shell of the oxygen atoms, right? Let's do that. So 1, 2, 3, 4, 5, 6, oxygen is done. 1, 2, 3, 4, 5, 6, oxygen is done. 1, 2, 3, 4, 5, 6, oxygen is done. And 1, 2, 3, 4, 5, 6, oxygen is done, right? But here comes the main part. You would think that sulfur is also done. The shell of the sulfur, the outermost shell of the sulfur is completed. It has 8 electrons, but no, that is where the statement comes into play. If possible, we'll try to maximize the number of bonds made by these atoms. You have to remember that. We have to remember that sulfur can make 6 bonds, right? Sulfur can make 6 bonds. And if possible, we'll try to make 6 bonds. How can we make 6 bonds? By converting these lone pairs to the atoms, like to the double bonds, right? Keep the symmetry open as much as possible. The final structure of sulfate ion is going to look like this. S double bond O, double bond O, 6 bonds with sulfur. Because it can make 6 bonds, it has vacant orbitals present. And then this is a structure of sulfate ion. It is going to have an overall charge of 2 minus, right? Similar formal charge calculations will be there. You can try doing it. This O will come out to be -1. This O will come out to be -1. And then these two will be the neutral oxygens, right? Fine. So that is like, these are some of the steps which we should follow. And you might have observed that we started very slow, but since we get hold of it, once we get hold of it, we're able to draw ozone. We are able to draw sulfate ions so quickly, right? So these steps are very useful, and literally, I'm telling you, you can draw any structures that is being asked to us in our exam. Okay, and once we draw the structure, we know how to draw the structure. We'll be able to tell the shape. We'll be able to tell the electron domain geometry. We will be able to tell the hybridization. We'll be able to tell whether it is polar or not. We will be able to tell literally everything about the molecule, right? Now we'll end it with one final structure, That is going to be phosphate ion, PO4 3 minus. Okay. Now we are going to draw it. Q is going to be 5 plus 4 times 6 minus 3, right? The charge we have to calculate, I think this is going to be 32 again. Rough structure we are going to draw. So let's do that. Phosphorus, 4 oxygens. Remaining electrons would be 32 minus 8, which is 24. Now we'll be using these 24 electrons to complete the shells. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All the oxygen atoms are done. But this phosphorus guy can make 5 bonds. Don't forget that, right? And we have to make those 5 bonds. One of those atoms will become double bond. And now the final structure is P double bond O, 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 O. Why am I sounding like Jadoo? Okay, so overall charge is going to be 3 minus. And you can definitely calculate the formal charges, right? Super easy method. Any structure you give me, I can draw it. And you guys can also draw it. Let me just show you. Let's draw H2SO4. I don't even need to make it and we do all the calculations now because I know sulfur can make 6 bonds, right? I'm going to give sulfur 6 bonds. Double bond O, double bond O, O, H, O, H. Now you must be thinking, how did I draw it so quickly? Because I'm following the process. I'm following the steps in my head. And that you guys can also do it once you know the steps and once you have practiced it enough and once you are confident in your skill level, or you can say you're confident in the practice that you have done. So that's the way to draw any dot and cross structure, any Lewis structure for covalent compounds, which is generally what students find tricky. And that is it for this class. I hope you liked it. I hope you understood everything. And I'll meet you guys in the next class, in which we'll be doing another important topics for your board exams. Thank you.